First-order logic has two sides. One side is the syntactical side. The other side is the semantical side. The syntax can be thought of as kind of a programming language for mathematical statements. In particular, it will answer questions like, what is a well-formed mathematical statement, thought of as a formal statement? And later on, we will also answer the question, what is a formal proof of a mathematical statement? So just to stick with the first question here, the syntax should answer a question like, looking at an expression like this, so for all x there exists a y such that x plus y is equal to 0, this, our syntax should classify as a well-formed statement, while something like that should not be classified as such. So the syntax should provide us with the rules that allow us to split or distinguish between well-formed mathematical statements and just statements that are nonsense. Semantics, on the other side, specifies the realm, or more precisely structure, over which formal statements are interpreted. So a realm, or such a structure as we will see, can be something like the integers or the real numbers, or something like the continuous functions on 0, 1, or some Hilbert space. The main thing is that the realm, or the structure, will provide us with a set over which we interpret our statements, but not only that, it also provides us with the corresponding structure on that set, such as an addition or a multiplicative structure or a function structure and so on, that allow us then to interpret the various function symbols, relation symbols, and so on. And depending on which realm we choose to interpret our statements over, we can get different outcomes. For example, if we look at this statement, right, from the slide before, if we interpret x and y over the realm of the natural numbers and plus s addition of natural numbers, this statement will not be valid, because except for 0, no natural number has an additive inverse, right? So over this realm, the statement would not be valid. However, if we interpret the statement over the realm of the integers and keep plus as addition as integer addition now, then this statement becomes valid. And the rules for semantics will specify exactly that. What is a structure, and how do we interpret precisely a statement over such a structure? Some of the fundamental questions that arise then concern the interplay between the syntactical side and the semantical side. So for example, once we have specified what a formal proof is, right, and we have defined what it means that a statement holds in a structure, right, then we can ask if a statement has a formal proof from some axioms. So this is a purely syntactical specification here. If that's true, is it true that this statement then is valid in every structure that satisfies the axioms? In the other direction, if a statement then is valid in every structure that satisfies the axiom, so that's a semantical property, does there exist a formal proof from the axioms? More formally, we will define this. We can express this as this property here. So this means provable, a fully formal property, and this means logically implies. This is a semantical property, and indeed it will turn out that these two properties are equivalent. And this is the content of the Gödel completeness theorem. We start by specifying the syntactical side, and at the basis of this is the notion of a first-order language. So think of a language as specifying the symbols that we are allowed to use when forming statements. And every such language comes with two parts. One part that all first-order languages share, and one that can be chosen depending on the mathematical context you want to describe. So those will have different symbols depending on whether you want to do field theory or linear algebra or analysis or graph theory or set theory. The definition of a first-order language is as follows. It's a set of symbols L composed of two disjoint subsets corresponding to the two parts. So the first part is the one common to all languages. We have a reservoir of variables, Vn. We have an equality symbol. We have logical connectives, negation and. We have an existential quantifier. And we have a pair of auxiliary symbols, parentheses. The second part of a language, this is called the signature, contains the symbols that we choose according to the context. It's denoted by sigma to the L, but often we'll just use L to denote also the signature. And it consists of the non-logical symbols of L. And there are three types of symbols. There's a set of constant symbols. It can be finite, it can be empty, it can be infinite, even uncountable. So we make no restriction, it just has to be a set of symbols. So those are the constant symbols. Then there's a sequence of sets f sub n to the L. The elements here are called the n-array function symbols. So for each arity, we have a set of symbols, function symbols. Again, for each n, this can be empty, finite, infinite, even uncountable. And similarly, we have a sequence of sets R sub n, and those elements are called the n-array relation symbols or predicate symbols. Let's look at a few examples of languages. So since the first part is common to all languages, we usually specify languages by just giving the second part. And we also don't usually split them up when we state a language in examples. We don't split them up in the different arity sets and so on, because those will usually be clear from the context. So for example, we have the empty language, where we don't have any symbols besides the standard ones, the common ones. So remember, we still have equal here, right? That's always present. Next, we have the language of orders that contains just one symbol, and this symbol is thought to be a binary relation symbol. Similarly, the language of sets also contains just one symbol, and again, it's a binary relation symbol, right? Because being element of something, that's a binary relation. Next, we have the language of matrices. So here we have 4 entries. This would be a constant symbol, and this is of course thought to represent the identity matrix. This would be a unary function, right? Taking the transpose of a matrix as a unary operator. Then we have plus and times, so this would be binary functions. And finally, we have here as an example the language of rings. This has 2 constant symbols and then 3 binary functions. Now that we have a reservoir of symbols, we can start building formulas and terms with it. So how exactly does that process work? So what do we build with the language? First, we build terms and then formulas. So terms would look like something like this. Terms would be sequences of symbols over our language that then can evaluate to an element of our domain. Once we fix a structure that we want to interpret this term over. Formulas then take terms as their building blocks and connect them using either relation symbols or, as in this case, equality, right? And these formulas then, depending on how we interpret the variables or assign values to variables, can have a truth value. So have or can have a truth value. So once we assign values from our domain to the variables, these will evaluate to a value in the domain, and this will also be interpreted as a value in the domain, and then we can determine whether that corresponding statement then is true or false in the domain, depending on whether we have equality here or not. Of course, there's also the case that we form a completely nonsensical sequence of symbols from our language, and our rules for terms and formulas consequently have to somewhat exclude us forming these. Let's start with the formal definition of terms then. So given a language L, we denote by L star the set of all finite sequences, or also called strings, over this language L. And given such a language, we set the set T to the L of L terms is defined to be the smallest subset D of L star, so of strings over L, containing all the variables in the variable set and all constant symbols, such that we have a closure property here that's satisfied, namely if we have an n-array function symbol and we have terms t1 up to tn in D, then this string, by just writing f t1 tn, also has to be in D. So that's the definition of the set of terms. So essentially the smallest set that contains all variables, all constant symbols, and is closed under this operation here, forming new terms using function symbols of the correct arity. However, we have to make sure really that D exists, because we're saying here that we take the smallest subset. So what about if there were no smallest such set, right? So please take a few minutes and try to verify or think of about why D exists. To increase readability, we will often write, as we are used to in mathematical practice, f of t1 up to tn using parentheses here, instead of that formal term here, right? In particular, if f is binary, we often follow also the usual use that we write t1 f t2, so we write the function symbol in the middle between the two terms instead of the formally correct notion f t1 t2. Right? So let's go over a few examples. Let's start with the language of rings. This would be a term. Of course, this is the formal term, which we will also use to prove certain properties about the syntax and the definition of terms and formulas and so on. But in the alternative notation, we would write it as this, that just increases readability for us. In particular, when it comes to something like this, here look at plus times v4, v2, 1. So that would be first take v4 and v2, right? Form a new term with those, v4 times v2, and then add this with 1, right? So this would be plus 1 here. You may already know this kind of notation known as Polish notation. Let's move on to the next example. Here we have a language of two symbols. This one is intended to be a unary function, just representing the exponential function. And this would be a binary function of some sort. We leave it open what this exactly means, because we're only concerned with the syntax right now. A corresponding term would be, for example, exp circ v1, v2. And of course, the alternative notation for that would be writing it exponential of v1 circ v2. Next example, language of matrices. Here we would have plus I t v3. Now, remember, here since t is a function symbol, we always write function symbols in front of, in the formal definition, we write it in front of the terms, right? So that would mean if we write it here, this function symbol would actually be applied to v3, right? But of course, in most often, the transpose of a matrix is written to the right. So this term would correspond in this alternative or more readable notation to identity plus v3 transpose. Finally, we have the language of sets. Well, there we don't have really a lot of examples of terms because we don't have function symbols. And we also don't have constants. So by the definition of the set of terms, the only terms that are really available to us are just pure variables, right? Now we move from terms to formulas. As I said before, terms are the building blocks for formulas, and we can use relation symbols or equality to connect terms to form formulas. So these two choices here give us the set of atomic formulas, namely formulas of the form T1 equals T2, where T1 and T2 are terms, or of the form R T1 Tn, where R is an n-array relation symbol in our language, and the T1 up to Tn, those are terms. So once we have the atomic formulas, we can then combine them using the logical connectives and the quantifiers. So if phi and psi are formulas and x is a variable symbol, so I'll often use now x, y, z also for variables, just to increase readability, so we don't have to carry that v subscript with us all the time. So if x is a variable, then this negation phi and psi, and here we need our auxiliary parentheses, and exists x phi, all of these are formulas. The full formal definition of the set of L formulas, formula L, is then following a similar closure condition like we had for terms. Namely, formally it is defined to be the smallest subset D of the set of all L strings, such that D contains all atomic formulas, as defined on the previous slide, and is also closed under the operation star. So if we look back here, this is the operation star, right? So we need to contain all of these atomic formulas, and then also be closed under taking negation, taking ands, and existential quantification. So, and similar to the set of L terms, one has to show that such a set D here as claimed here actually exists. So again, please take a few minutes to think about how we could formally show that such a set exists. And we will also use a number of abbreviations so that we can introduce more symbols that strictly are not part of our language formally, but they will allow us often to make formulas that we consider much shorter. So in particular, we introduce more logical connectives. So we look at OR, which is just a shorthand. So formally just a shorthand for this formula here. So whenever we see this symbol, we just replace it with this formula here. And of course, that's intended to be the disjunction of two formulas and an logical OR. There's the implication, which is, if you read this, the definition above, of course, is then equivalent to not phi or psi, right? And that's the logical connection or implication operator. Then we have equivalence, which is just implies, and phi implies psi, and psi implies phi. I see I have a little bit of too many symbols here, so let's quickly delete that. And then finally, we have the universal quantifier. So what does it mean that something holds for all x? Well, that means that there does not exist an x such that not phi holds. Right? So we use this again as a shorthand for this, and of course that gives us the, in semantic terms, the universal quantifier. Let's conclude this lecture with a few examples. So here we have the language of rings, and the formula would be for all x, not x equal to 0, that implies there exists a y such that x times y is equal to 1. So this, of course, says if x is not 0, then it has a multiplicative inverse. And you can already think about like contexts for when this formula would be true and when not, right? And for example, it will not be true when interpreted over the ring of integers, but if you interpret it over the rationals or the reals, this formula will be evaluated to true. In the language of orders, right, we have the following formula here that expresses just that the order or that the binary relation is transitive. And finally, here's a language of lattices where we have we haven't seen that one before. So this would be a unary function symbol. Then we have these two would be two binary functions in a lattice. As you can see here, it's using our more readable notation. If we really wanted to write it as correct terms, formally correct terms, we would have to write it like this. But this just says that the lattice satisfies De Morgan's law.